Hello, gentle readers, fellow earthlings. June 3, 2026. Reading Foundations today with Ross Finlayson, myself, will be the latest installment in a series of video essays. These sorts episodes in the development of unspoken narrative and unscripted account, yet rather deliberate and after much contemplation about foundations, the theory of everything. There's going to be one good theory at all, is there? And this is the idea that there is. It's true, and and we can agree to it. It's foundations. The vera-theatheory, truth, and the certi-theatheory, the concordance. These are the accounts of that. Then the objects of the universe of the domain of discourse of mathematics and logic largely exist, and we discover them and describe them and give them names, not just make up names. So it's a kind of structuralist realism with nominalist fictionalism as just an example of making theories. And then for an account of ontological commitment, of the ontological status of the ontological activity, the theory has that there is one, and it's real, and so thusly it has a lot of responsibilities to be free of paradoxes, to be constant, consistent, complete, and concrete. A theory for reason, the reason, the rationality of the natural and the real, de res, de ratio, de natura, de re, of the continuous and the infinite, de continuo, those being Latin sorts of phrases, just being of or on. Here, continuity. For infinity and continuity is primary in the theory. A paleo-classical and postmodern account. There is one at all. Last time we were reading from this book of Hans Reichenbach, Philosophic Foundations of Quantum Mechanics. And what that led to being was mostly an account of statistics and probability theory. In statistics and probability theory, the theory is very much like science, the account of statistics. There's a hypothesis, usually a null hypothesis and an alternative hypothesis. Much like in scientific theories, there's a before theory and an after theory. For the account of dialectic, the thesis, antithesis, and synthesis, that the scientific and statistical accounts are much alike, and the philosophy is about the same. Meaning we never really prove anything was according to the scientific theory, only didn't disprove it. So weighing two alternative theories, then with usual ideas that besides reproducibility and observability and falsifiability of the theory, that means in science, what science is according to the theory, the philosophy, and the scientific method. Or for probability's sake, there's the same sort of account, repeatability, observability, and falsifiability. And then for models of laws of numbers, making for counting arguments for distributions of a random distribution. Or here, as from the scientific side, a theory we can appertain to, if not quite attain, for what mathematics then in logic we can obtain, these sorts of accounts. As mostly the reading of the book here on the probabilistic interpretation of quantum theory was about probability and statistics. And so it's not necessarily the result of the study of quantum dynamics that it's a discrete quantum dynamics, nor that it's an indeterminate quantum mechanics. So here there's a continuous quantum mechanics and a deterministic quantum mechanics. And that doesn't obviate or make obsolete the ideas of free will or the emergence of behavior. Whereas for the behavior as alike, from what we can measure and detail, a random distribution doesn't mean there's not randomness. It just means that there is causality. and then randomness is just kind of observed and emergent, and similarly free will is unfalsifiable. So the responsibilities and possibilities of free will just still exist. So we don't need an indeterministic theory to make for accounts of action and the uniqueness of events in the world. There is a causality and a truth, and it's just so that everybody has their own account of it. And then that when it comes to measurements, like for the quantum theory and the science of the things, it just happens to be kind of convenient that a modeling the emergence, the behavior of what are theorized to be particles is simplified by making probabilistic accounts, when otherwise it would involve a superclassical account that the waves and for spin and for the quantum analogs of classical properties and descriptions, momentum, spin, even color in the nuclear forces, has that those are just superclassical in the fact that they basically go infinitely fast. And so from the account of Born, Max Born, and Feynman, Richard Feynman, about the claims that when they get to studying the theories, they necessarily arrive upon notions like the self-energy, which is basically reciprocation and oscillation, or the renormalizability of theories, meaning that there's infinities and continuity that were left aside in making the truncations for the commutativity relations and these kinds of things. That Born and Feynman, of course, reflect upon that. These are the things that go into why it's convenient description to have a probabilistic account of quantum mechanics, but it's not as necessarily causal or explanatory. And so I'd wonder whether Reichenbach basically gets into, in the discussion of the philosophic foundations of quantum mechanics, as per the title of this book, whether he addresses these same sorts of accounts and has a superclassical explanatory setting, where the superclassical's promontory aspects sort of rival Zeno and the notions rather of motion, the notion of motion. And as for motion and moments here, or about time, the continuous nature of time. Getting back in this book a little bit, then I'd look to the table of contents and see if there's something about which there is to be describing why it is a causal and overall a classical account of the quantum mechanics, and then those being simply in matters of scale and the atomic scale. That also being sort of its own conceit, that there's a graininess or particular account of nature when it's ultimately smooth and infinitely divisible, like time is. That taking these sorts of accounts can help a lot when otherwise people, when they're introduced to the formalisms and that, well, here's our particles and they act by forces and live in this theory, when it's really waves in the fields, the potentialistic setting, that's the real theory. Then later they wouldn't be dissatisfied or dissuaded from what were their interpretations of their intuitions so developed that were incomplete. And so the idea of having the superclassical results first, as for motion and time, and for continuity and infinity, help a lot to make so then everything else just sits inside of that, instead of that that's always outside. Otherwise, these accounts, which not just makes them ignorant, but even unawares. So at the end of this book on part 3, it says it has a comparison of classical and quantum mechanical statistics, and it's getting into the corpuscle interpretation or the particle interpretation, and then the wave interpretation, the impossibility of a chain structure. And now I'd imagine that would reflect on the number line and how it's a continuous, so that besides that in any given particular region it's infinitely divisible, that in the infinitesimal neighborhoods of the contiguity it is a chain, and that makes for like the path integral and stuff like that. And then it gets into accounts of logic saying, oh well, it's not a yes or no thing. It's an opening, a perestroika, a catastrophe. So we'll just say we have three values of logic. Well, maybe the account is you just need two tables, which ones do hold and which ones don't. It's kind of like in the account of cosmology, and when they're taking data samples from all the points in the sky. And so they get to something like, well, here's the column in the table for redshift. This is how far this particular object in this particular part of the sky appears to be receding. And they originally built that after discovering, it says, well, everything appears to be receding, or 99% at least. And now these days they know that it's not. It's like 51%, 49%. It entirely boggles the previous interpretations and all the data, because both Big Bang and steady state fit the data somehow, and neither is really falsifiable. They're as scientific theories, they're really accounts of stellar evolution, and then for classical mechanics and Newtonian mechanics and relativistic dynamics. All those theories kind of put together. It still has it then in this column in the table where they put the value, kind of like in a true-false truth table. Where do you put the value for don't know or don't care, or otherwise unknown, like Lucasiewicz's U, true, false, and U for unknown. Has that then, the account then over this multivalent, multivalued logic, has that instead of having like the points and dots in the middle, that's all the structure that is embodiment of the relations, the model of the thing, that there would be a separate table, whereas like these are the numbers that mean this column that's like the percent hydrogen or pH value of acidity and alkalinity is for redshift, and it's always usually thusly onto one side, the other 7 with regards to the log scale and numbers on the pH scale between 2 and 14, say. That's a statistical account, because past 7 standard deviations, 7 on either side, that just makes for accounts of the statistical mechanics, where it comes from, why the numbers like those range like they do. So anyways, in this table, then they have all sorts of numbers in there, and they're usually simple and clear in the sense of that they're unambiguous. When they aren't, they had to put in the same column. It's like, well, this is actually on the low side, and it means the opposite. Or it means that it's on the high side and it means double. Because that's where these statistical, as they would be, outliers lay after the development from the theory of pH, that being a reflection about the mean, and then the central limit theorem and the accounts in about and around that. So much like the multi-valued logic gets involved when there's unknowns, it also gets involved when there's the data had loss. So there was loss in the data. And so then trying to put that back together and make for accounts of why it's so, that the statistical interpretation gets reinterpreted is not just besides the central limit theorem isn't the only limit theorem in town, with uniformization limit theorem and polar limit theorems, and not just besides that the account of the measurements that arrive for things like the cosmological redshift are biased, distorted, as they call it. The redshift bias and redshift distortion are the modern accounts of trying to explain why otherwise the universe has reached 7 sigmas or 7 standard deviations, why it's all dark energy for the light's account, or all dark matter for matter's account, neither of which can be so in the theory. Neither of which can be so. For lambda, or cold lambda CDM, lambda cold dark matter accounts, usually, like, for example, 85, what's that? Well, it's just 1 standard deviation. These are the accounts of how the numbers get fudged to fit the data to the theory. And so when in talking about the accounts of the flex of the things, is that they don't fit. And so then when Reichenbach is getting into why and why not the classical action and the linear is and isn't part of the particle and wave model, and similarly then for the logic saying, well, this is account even lower level in our mathematical logic, how otherwise we'd have to break what was laid out as the setting for the relations of these things, as it is all reparable. It's repaired by accounts for classical motion, making for why the rotational can have a distinction from the linear, for space contraction linear and space contraction rotational, that the Galilean past the first and second order for momentum, the integral of inertia, not the other way around, has it that there's room in the theory which has these theories are already only good to the first or second order as approximations, as truncations, this reduction, cancellation, reduction, correction, these reductions, approximations, reductions, truncations, that fitting that up and together can then make for why dark energy hasn't broken physics in the model of cosmology, and dark matter hasn't broken physics in the model of galactic scale and gravity and all these kinds of things. And gravity, which doesn't even exist in the theories of general relativity nor quantum mechanics, both of which are just said to somehow be current all the time, because putting in a theory would violate the energy budget everywhere at once all the time. Perpetual motion has that. So we might look then to Reichenbach's accounts and see if he's talking about the infinite visibility of the field, and then see if he's talking about the particle and wave interpretation. So back here on page 111, nature of probabilities ends the previous chapter. Potential probabilities. The hypothetical manner of the introduction, however, does not make them probabilities of another kind. Expressions like potential probabilities, sometimes used to distinguish these probabilities from other probabilities, must appear inadequate. So the account that a potential theory is a real theory is the same since Lagrange. He's like, well, that's the potential and actual, or the potential and real forces must sum to zero to make an account of balance of the budget of the things. And then the idea then that it's overall a potentialistic setting has that is action at a distance. And so it's the field theory instead of the force theory for these F-Lorentzians, any one of which makes a model of relativity theory, including a doubly objective model of relativity, which also entertains absolutes in space and motion. Again, that Reichenbach's mention of these potential probabilities is that this is part of the section nature of probabilities under mathematical outlines. Examples of such theoretically introduced probabilities are given by the statement that the probability of a given face of a die is 1 to 6, so that all arrangements of molecules in Boltzmann-Maxwell gas are equally probable. Such statements sometimes have been considered as derivable a priori by means of a principle of no reason to the contrary, which is assumed to constitute a part of the calculus of probability. This is, of course, an untenable conception. So here, for counting arguments, then laws of large numbers, there's at least 3 laws of large numbers, and there's 3 continuous domains and 3 Cantor spaces. And so there's reasons to arrive at why things like the martingale, that of double or nothing until you win or lose, usually the idea being that you go bust before the bank, the martingale, the gambler's dilemma, then has that there are counts where you win and counts where you don't, and then it counts where it just goes on forever. So that's similar then with these descriptions here of the a priori probabilities, whether it's like the central limit theorem, or usually people would think it's like just everything's average, or uniform limit theorem, uniformization limit theorem. And otherwise for the polar limit theorems, it's like usually the idea is like it's something else, it's not in the middle. Any of these kinds of accounts of what then makes for the sample space and the laws of large numbers, the counting arguments, and then the accounts of analysis that make continuous distributions besides discrete distributions, and then not the Bayesian and the Knightian, and after the Jeffreys and the uncertainties besides the chances, has that these are the sorts of things that Reichenbach at least considers. And so that's good to know, because then that way otherwise it would just have been just outmoded and obsolete. About individuals and infinite populations. Keeping to the results of these general considerations, we now can understand a physical distinction which must be made with respect to statistical assemblages occurring in quantum mechanics, known as the distinction between the pure case and the mixture. The nature of this distinction may be made clear by the following considerations. Let's talk about eigensystems, which are like functions, and finding ways to then use accounts of Lagrange and Gauss and matrix manipulations to result for some systems of linear equations, various forms of solutions, the determinantal analysis often, eigensystems, Sturm-Liouville, a bunch of different related things. Each of the eigenvalues corresponds to a specific eigenfunction. We then collect in one class C all those cases in which we obtained the mu I. This assemblage is said to constitute a pure case. It's so called because if we would repeat our measurement of U in this case class, we should find ui in each of the systems. Now imagine we make a measurement of a non-commutative entity V on all systems of C. We then shall obtain in one system the value V sub k, and another value V sub m, etc. Probability is of these values being determined by a reference formula in section 22. After this measurement, the assemblage C no longer constitutes a pure case, but a mixture. So this contains systems with different values of V. And so that gets into, for example, the difference between the central limit theorem and the polar limit theorem and how they would add up to be the uniformization limit theorem, or whether the uniformization limit theorem breaks in and out for inner and outer products to make the central limit theorem and the polar limit theorem. So here, that goes in, and then how things would be adding up probability amplitudes, the real parts, if already in Hilbert space it was given to be all complex valued, and then kind of taking the square and the root of the real part of that to arrive at what's being added up here. The field number formalisms, field occupation numbers, these quantum properties, these quantum values, that Reichenbach is saying, hey, it's got to be averaged over. It's a mixture. Basically, the pure case is really just kind of the pointwise case, which doesn't really apply in any setting of more than one points, or in a sense 2 points. The big difference between 2 and the pairwise and 3 or more, the multi or n-body system that these systems are meant to address. So this goes for both the statistical ensemble and its developments and derivations, because all that was described there is used for gas laws and stuff like that, not quantum. And then also apply to the quantum, because then in Braun-Ket for the Hamiltonian, there's just given Hamilton, then Jacobi, and then Dirac's account for Braun-Ket, and the Heisenberg and the Schroedinger pictures. One being kind of for the classical point-like, and the other being for the classical wave-like. Why that is so. These considerations will serve to clarify a terminology frequently used with respect to individual systems. When we say that a measurement on an individual system creates a pure case or reduces the psi function of the system to an eigenfunction of the measured entity, we mean that such will be the psi function of an assemblage constructed by putting into one class the system considered and a number of other systems with the same result of the measurement. The latter class constitutes the reference class. See also the remarks at the end of section 20, which is understood in the expression psi function of an individual system after a measurement. This phrase, therefore, means the same as psi function of a class of systems after a measurement of U with the result U sub I. Whereas the assemblage representing a pure case consists of systems each having the same psi function, namely a psi function given by the eigenfunction psi or phi sub I q, or f sub I q, q and p usually being for the momentum operators of the Heisenberg picture with indeterminacy in the linear, and the Schrodinger picture with the wave function and collapse. Phi q, the subscript I being the same for all systems. The mixture includes systems of various forms of psi functions, namely functions phi sub k q with the various subscripts k. Each function phi sub k q will be realized in a certain percentage c sub k of cases. Now both assemblages are only statistical assemblages, since even in the pure case, the results of measurements of an entity v having an eigenfunction different from the psi function can only be statistically predicted. So here there's an account that the pure case is as actually the the sort of emergent case, not the base case of these things. The idea that the various mixtures make what looks like a flat line instead of a bump, or vice versa. These are the accounts of why getting into probability and then summing those over areas is when each of the pointwise possibilities is independent. Has that this is kind of what's going on in this account here. Now both assemblages are only statistical assemblages. Is it possible to characterize the mixture by analogy with a pure case in terms of one function phi or psi sub q? This function, of course, would have to be different from each of the eigenfunctions phi sub k q. And then in considering an answer to that, it's about matroids. So matroids kind of live as about a matrix. A matroid has edges, and they can kind of curve up and go around. For example, like a torus or something like that. So there are accounts then to be made for, well, how does that make an eigensystem and eigenfunctions? It's kind of like the account for the study of harmonic functions, those functions that are Laplacian, meaning a sum of second partials on the left-hand side, equaling 0. And then that some people say that potential theory is, in the study of potentials, is like the study of harmonic functions. But there are lots of accounts about where that is an incomplete description of what are the potential fields. So the study of potentials then here is similar to the study of this eigensystems, and whether there are extraordinary or superstandard and non-standard eigensystems, matroid eigensystems, say, where it is so that then these accounts of the analysis still make for the determinantal analysis in the middle, that the classical account is the sum of all the potential accounts, not vice versa. And so a measurement is just a very, very localized account compared to everything around it. So the author says, can it be so that the mixtures can have eigensystems, and so to treat them as like linearized, as for Poincaré completion, and then to keep them though well formed in the sense of Hadamard is about the differential analysis. Here has that the differential and the differ-integro and the integro-differ and the integral analysis always live together. And so then having the Duhamel term is nominally non-zero, and besides in pure systems as there would be that are entirely defined by a differential or an integral term, all the mixed systems are the real systems. And so these are the accounts of why then for after Duhamel principle and then for Parseval and Plancherel, then make it for L'Hopital and Rodriguez is kind of an out from that, meaning a way to reduce to a close form. That these are usual considerations, what get involved, and then all this necessary accoutrement of the development, deconstructing the arithmetic and the analysis to then give for algebra. So we can just write symbols like phi and psi and make determinantal settings for algebraic treatment of via matrix methods. The determinantal analysis, algebra, has that, yes, there is an affirmative answer to Reichenbach's question, and not many people ever get that far. And it says the answer is negative. It is not possible to characterize a mixture in terms of one psi function. We prove this by assuming there is one such psi function, showing the assumption leads to contradictions of the kind explained in section 22. Let us denote the mixture by S. If there is a psi function of the mixture S, it can be expanded in the eigenfunctions phi sub k of q. Psi of q equals the sum over the k, so the sigma k is the phi k is the q's. So those being coefficients, then those would be those are the amplitudes. According to Rule 2:17, the value sigma sub k, its absolute value squared, represents the probability of measuring the value u sub k of the entity u. Since the result will be found in all those cases in which the individual system is represented by the eigenfunction phi sub k of q, we have the probability of S dot m sub u comma u sub k equals the square of the sigma k equals ck. Now let us consider the question of measurements not of the entities u or v, but of another entity w with the eigenfunctions eta, m, q. Writing psi in these eigenfunctions, we have a 24 section 11 psi q equals the sum of the m's of the rho sub m's eta, m, q. And therefore, with the use of formula 25 from section 11, the probability is s dot mw w sub m equals rho sub m squared equals sum over the k's of the sigma k mu or v km's. There are letters in the Greek alphabet that then sometimes have extra scripts that it would help to have, that there are some extra characters usually according to language. This is from about the 1940s or so. Squared. So you got squared, and root means square, and these sorts of things. So it's building an account of how those are to be keeping the triangle rule or Cauchy-Schwarz inequality, so a metric and the norm being the same when length and distance really are two different things. One travels through the other in time. And then for otherwise the accounts, then when this is like when it is in a line and it's in a box, vis-a-vis the rotational or this or that the matroid is given the affirmative answer before would basically tend to include. And then whether that's yet an eigenfunction is in the inside is still there to be figured out. On the other hand, this probability can be determined as follows, writing phi sub k in the eigenfunctions eta sub m we have with formula 26, section 11. The phi sub k q is the sum of the over the m's of these mu km eta m q's. And so it's taking the cross or the cross either way. Since the probability to have the eigenfunction phi sub k of q in the mixture S is given by ck, we have the probability equals the sum over the ck's again. So these constants have they have implicits, and so they have terms, and they might have interacting terms. But here, after it gets through this dot product here and taking the scalar account of the mu sub km squared, and that equals the sum of the sigma k squared dot the mu km dot squared. We are here led here to the same kind of contradiction as presented by 8 section 22 and 12 section 22. Although there are exceptional matrices mu sub kn which satisfy both 4 and 6, most unitary matrices u sub km will not do so. In other words, it is always possible to construct a unitary matrix v sub km or what is the same to define an entity w for which 4 and 6 are not compatible. And then that was with regards to unitarity, complementary, and orthogonality. Those always have to hold, making for the affine and the conformal and the magnitudes and the right angles and straight lines and these kinds of things. And so then when these properties are ascribed into various considerations where they do and don't hold or where they flex about interacting terms, is like to show why there's a view that the end result is the inner or outer product, and those being reversed. So, and then to generate a contradiction, Reichenbach says, then it follows that it is not permissible to consider the assemblage S as characterized by one psi function. So whether they would have to have two psi functions, whether it had degenerate psi functions, meaning or the pseudo psi functions, and why and where it is that those hold together in the corners or in the main for the corner and edge cases is for the tiling, the field of these things. That these are accounts then carrying on. The assemblage S can be characterized only by a mixture of psi functions. So the idea, as mentioned before, about kind of just reversing the way those are added up is that that whether or not that is a pure or a mixture of the psi functions, the eigensystem with the one eigenfunction here. That satisfies the relations maintaining the orthogonality, complementarity, and unitarity is for why these are distinctness results then, vis-a-vis uniqueness results. I'd give it as an example something like the theorem from abstract algebra, where it's arrived at the reals as the complete ordered field are the only unique complete ordered field up to isomorphism, as it said. So that C, the complex numbers, are given to also be the same. Now, besides showing that complex numbers have at least two definitions of division, and so thusly they have two definitions of products under inverses, and just one of those is picked, just like saying, well, negative numbers don't exist in positive numbers, or imaginary numbers don't exist in real numbers. Branches in a multiplicity theory. That talking about analyticity, and then the uniqueness of the isomorphism, or up to isomorphism from group theory about algebras and the complete order field. Also, negative 1 to 1, the interval, can be equipped with field operations itself, and then that's basically is put that in a box, and it's not the same. It makes it what was a uniqueness result now just a distinctness result. And so what was a closure and a principal branch, ignoring the other ones, is not left alone like that anymore, although it can be considered in its own case in the contemplation and deliberation of the thing. So then here for the account here that is of the uniqueness as it was set up of the unitarity, say, as that's in an account of the superclassical, and an account where the mixture functions are what result to pure functions, kind of like that out of tones emerge a note instead of that out of notes emerge a tone. Has that for similarly here for the account of whether electromagnetic radiation is compounded refraction, whereas light is pure diffraction. That these are accounts then to help provide to people who would otherwise have to follow the arguments of Reichenbach and is kind of between Born and Feynman, that there are ways to make it so that then this can be kept in place. So this is before then the account where it gets into the mathematical appendix as with regards to the particle conceit, the wave conceit, the chain or path, and these kinds of things. And then, according to Reichenbach, everything would be a mixture or pure, is the idea. The peculiarity derives from the fact that, emphasis the authors, the pure case represents the utmost degree of homogeneity attainable in quantum physics. This case may therefore be considered as defining one specific physical situation. It's an image. The present section concludes our short exposition of the mathematical methods of quantum mechanics. Summarizing, we may enumerate as the basic principles of quantum mechanical method the following principles. 1. The characterization of physical entities in a given context by operators, eigenfunctions, and eigenvalues determined by the first Schrodinger equation. 2. The characterization of the physical situation by a function psi, which through the rules 1 through 3 in section 17 determines the probability distributions and is inversely determined by these distributions. Section 20. Number 3, the law of the time dependence of psi given in the second Schrodinger equation, section 18, and 4, the quantum mechanical definition of measurement, section 21. The principle of indeterminacy and the disturbance of the object by the measurement are not included in these basic principles. They constitute derivable principles since they are derivable from the basic principles. So time dependence is classical. The Schrodinger equation determines the probability distributions and is inversely determined by these distributions. So as when they go to infinity, that they go to 0, or vice versa, the inversion account. And the quantum mechanical definition of measurement. So kind of like Einstein's account of the Lorentzian, the Laplacian of space terms minus Laplacian of time terms equals the Laplacian of the metric. any system was so satisfying that for invariant theory makes so a model of relativity theory. Reichenbach would say that anything that makes real wave collapse and exhibiting what can be described as by a probabilistic account also is quantum mechanics. So it definitely doesn't exclude continuous quantum mechanics nor deterministic quantum mechanics. It just says it's too fast to measure. Interpretations, page 111. Comparison of classical and quantum mechanical statistics. Now let us consider a generalization, which may be called classical statistical physics, and which consists in a combination of causal laws with statistical methods. In this case, we consider the causal laws 1 through 3 as still valid. We introduce, however, a method which takes into account the fact that the values Q sub naught and P sub naught cannot be exactly measured. Nothing can really be exactly measured. There can be counts of discrete items and elements, but in the accounts of the real value and the continuously variable, it's approximations, correlations. And then the account of that. It's still classical. The mechanics of the things, it's just so usual vis-a-vis measurement and the contrivances of a measurement. Yeah, I mean, if you had the entire universe as a blank, empty experimental setting and it made one spark, it would be measured as one spark. Yet about the individuals and infinite populations, the author here is describing then to make that as difference between classical and the quantum, where the causal laws are still valid, but we just don't know exactly what we can expect to measure. That the specification of these values is therefore replaced by the statement of their probability distributions. And then there's to be mentioned that the sampling effect or the observer effect in interfering with a system of quantum measurables, the sampling, observation, and measurement effects are not just about the limits of the precision of measure and aren't just about the superclassical speed of light. For example, that these are mixtures then which make these kind of pure probability amplitudes left over, these particles. There's a deconstructive account for that as well. We write these distributions at the time t naught in the form d naught, d naught, and d naught of q, p, and qp. The latter function giving the probability of combinations of values q and p. The table of derivative relations of classical statistical physics then can be written as follows. Given 1, the probability distribution d naught q, comma p at the time t naught, 2, the physical laws. Determine 3, the probability distributions of dq and dp, and the probability distributions du of every other entity concerned at the time t. For the probability distributions of d sub t qp at the time t. 5, the probability distributions dt d of q and dt of p, and the probability distributions dt of u of every other entity concerned at the time. Comparing this table with that of the strictly causal case, we'll see that the occurrence of probability distributions involves a further distinction which originates from the distinction between d naught of q, comma p on the one side and d naught of q and d naught of p on the other side, interacting terms. The first distribution appears in the category what must be given. The latter two distributions appear in the category what is determined. So this is a reflection on making for so that it evinces that this characterizes the wave behavior. And these terms don't really say yet what they are, kind of like Riemann tensors don't say what gravity is or how to calculate it. They just say what it has to fulfill being when it's done. The derivation of the latter two distributions is achieved through the relations. The d naught of q is the integral of the d naught of qp dp, and the d naught of p equals the integral of the d naught qp dq. So that's taken into account of the analysis, and then the distribution being so partial, because it's taken the integral in either of the other terms, and so it's got two variables, yet it's only a univariate term, and so it's partial. It's merely partial. And then reflecting on that, the reverse, that's just writing the partial relation of the partial differential in reverse for the operator. And so that's a reduction cancellation of that results a reduction truncation. So it is important to realize that this determination cannot be reversed, i.e. that the distribution of d naught qp of the combinations is not determined merely by the individual distributions. Only in case we know that q and p are represent independent entities can we write d naught of q comma p equals d naught q dot d naught p. That it's the product of those is by a scalar multiple, these probability distributions and also their values. But the application of the specific theorem, or the special theorem of multiplication expressed in 6, the dot product, presupposes some definite physical knowledge about the independence of q and p. Without such additional knowledge, the function d naught of qp must be directly given and in general will not have a special form. On the other hand, if neither such additional knowledge nor statement of the function of d naught qp is available, that being the probabilities of both the momentum operators, momentum and the amplitudes, the knowledge of the distributions d naught q and d naught p alone will not be sufficient. So that's just giving that, yeah, there's limitations to the expressions because the tractability gain for the fungibility gain by making it a partial account, so it's simple to make the expression, is lost that much detail. So it'd be said then that the accounts of the total differential analysis and the singular integral analysis are a bit more involved than the partial differential analysis and the plane curves of the integral analysis. Then the integro-differ and differ-integro accounts are even more total than that. So that's then describing, then derivations follow, meaning of the operators, no equivalent in the strictly causal case. The relations between the terms represent direct generalizations of the causal case. So they'd also be recovered by having a causal case. Determines the probability state of the system, and with this it determines the physical situation of the system as completely as it is possible in quantum mechanics. In discrete, indeterministic quantum mechanics, there's a continuous deterministic quantum mechanics where it could be more complete and yet it is according to quantum mechanics. We therefore can summarize the derivative relations of quantum mechanics in the following table. So as we had the derivative relations of classical statistical physics as above, which was this state at all times being known. And then for the quantum, it says, given 1, the complex function psi naught of q at the time t, 2, the physical laws, those being given. Determined, 3, the probability distribution and the probability distribution of other entity concerned at the time t naught. 4, the complex function psi sub t of q at the time t. And 5, the probability distribution is d sub t of q, d sub t of p, and the probability distribution d sub t of u of every other entity concerned at the time t. Physical laws mentioned in 2 include, with respect to points 3 and 5, the rules for the construction of operators under the first Schrodinger equation. In addition, rules 1, 3, section 17, determine the probability distributions with regards to point 4. We include the second Schrodinger equation in the physical laws. So wave collapse, and then here that it gets involved with the stop derivative and these other kinds of accounts of what would make mathematically so to be like so, and it's going to be discovered a little bit more later about how to make then for these requirements of the theory that then in these mathematical forms, similarly for the the fields and forces there, Lorentzians, any model of relativity theory, here these quantum derived amplitudes, in a sense, the relations of state and motion and state are to be classical quantum again, super classical quantum. So that would be here. That would be for reading the first and second Schrodinger equations and then figure out what's going on with them and making a deconstructive account of them. Where for Reichenbach, then that would give a model of what can be derived to be said what is quantum theory. All right. Oh, so the chain then might be for the causal chain. First is the answer will depend on the meaning assumed for the term causal law. This term usually includes two distinct conditions. First, it is required that the cause determine the effect univocally. Second, it is demanded that the effect spread continuously through space, following the principle of action by contact. The latter condition is frequently expressed by the term causal chain. Anticipating our results, we may say here that our answer will be negative. We shall find it impossible to interpret quantum mechanical relations completely in terms of causal chains. They still have them, though. This is the kind of the account of the Heisenberg certainty vis-a-vis the Heisenberg uncertainty, that particles always have position and momentum vis-a-vis not being able to know both of them so precisely at the same time with regards to each other. We shall be led to the result, however, that it is even impossible to interpolate such probability chains by way of definitions between the observable data of quantum mechanics. This negative result, which represents a statement of the whole class of equivalent descriptions, excludes the introduction of causality in any sense into the world of quantum mechanical objects and thus establishes the principle of anomaly formulated in 8. Here there's a counterclaim that instead is just extra local. And so that would be any account of entanglement of particles or confinement of particles or really any account of making for, as Reichenbach put it, a negative result about the observable data of quantum mechanics in the world of quantum mechanics, that his definition was always already local. And so that's not so in terms of what a causal chain would be, because the cause of these effects is still in effect. Then section 25 is the corpuscle interpretation. Every interpretation which coordinates to a measured value q, one simultaneous value p, and vice versa, may be called a corpuscle interpretation. It's a particle. Yeah. That's an observable, the idea, and then that's the force carrier. Then that is what moves about wherever there is its expression is what would be a chain or path. Is the path integral, this causal chain is together. It's a particle, and then whether it's so that it actually is a dot, or it's a wave packet, or that it's always a body and not just a point, vis-a-vis the point, local, global, and total, has that. It can also be read as a wave. So then getting to where there's the idea to read about the causal chain, he has to show, we can show that our rule does not contradict our previous rules. The relation 9 states that the value w sub m is independent of an unmeasured value v sub k. Relative probability is previously introduced, such as 15 in section 22 or 22 in section 22, state a dependence of w sub m on a measured value v sub k, vis-a-vis an unmeasured value. With the definitions 1 and 2, we have given an interpretation which is exhaustive, i.e. in which statements about unobserved entities, including simultaneous values, can be made. Using a terminology introduced in the general theory of meaning, cf. the author's experience and prediction, Reichenbach, we can say that in this interpretation, statements about simultaneous values of non-commutative entities have truth meaning for situations between two measurements and probability meaning for general situations. This distinction expresses the fact that for the latter case, we have defined only the probability of the values of the entities, whereas in the first case, the values themselves are defined. So the probabilistic account is partial and incomplete, and the other one just has its unknowns with regards to these mathematical formalism. So in the impossibility of a chain structure, after the corpuscle interpretation has been established as an admissible interpretation, we can ask the question of the consequences of this interpretation. It is in particular the question of causality which interests us. We saw that in the classical statistical conception there are causal laws which connect the states Q, P with future states and with the other entities U. Are there similar laws introduced with our corpuscle interpretation? No. A short analysis shows that this is not the case. And I said no because they don't have any other extra character than that. Let us assume a sequence of values, introduce a probability. So it's just saying then that the chain structure would to not exist. That saying that that's not the corpuscle interpretation doesn't have any new laws doesn't mean it doesn't have a chain structure, because those previous laws already kind of had a chain structure with regards to the account where I disagreed with Reichenbach before. Now, when I heard about Reichenbach before, I was reading the Dictionary of the History of Math and Science. And then when I read about his law of large numbers as the law of small numbers, and then how that's so effective and gives, at least it's infinite for probability theory, I still disagreed with that because it's not complete. It's in a sense has a completion result, but it's not replete. So that said, then now reading some more about this great account of quantum mechanics. So this Reichenbach's account of quantum mechanics, the theory, goes right on the shelf with the 20th century tradition and everything about quantum mechanics and its formalisms. Still has, and then at least it's possible to make deconstructive accounts and come up with some reasons why. Then what are declared here as agreeably and arguably terms and definitions and their derivations that hold good. And then as with regard to what the laws are of these systems, of these physics, still has that's it's also addressed, including where it's appreciated, that the author points out that there are choices made to prevent the mistakes being made, yet extrapolating those is mistakes. So that then we can go back and revisit these derivations, and it provides a way to have a fuller complement. Because is like they say sometime when they're not busy computing, quantum theorists will say something like quantum mechanics is never wrong. If you get it wrong, you're doing it wrong. That's the idea is that somehow the theory that's reduced to what is here pretty much. And as after Born's commutativity laws and anti-commutativity and non-commutativity, the non-standard, the non-classical, somehow it must be true, it must be causal, and it must be correct then in these sorts of accounts. Quantum mechanics is never wrong. Continuous quantum mechanics is also never wrong. The term chain structure therefore characterizes a structure in which the probability of value U is determined if the values Q and P are given. So we had the mention of the idea before, the interacting terms, and then also the classical terms, and yes, it is usually so given that the chain structure is like so. And then for the derivation of the path integral, which is like, what does it add up that we get what we see in the experiments? That also is a chain structure. As from reading from Swanson's the path integral and the derivations after Tominaga and Schwinger and then Feynman and these sorts of things. After a decade or so after this, our results show that we cannot even construct probability chains in the sense defined. And it's become point-like and it needs to be aligned. Is the idea. See also the author's Wahrscheinlichkeitslehre. Truth, like book theory. Chain structure, and then briefly about waves, the wave interpretation. The duality of wave and corpuscle interpretation is based on the equivalence of the function psi q on the one side and pairs of suitably chosen probability functions on the other side. It's always a mixture. In the corpuscle interpretation, the probability functions are considered as directly physically meaningful, whereas the function of psi appears only as a mathematical abbreviation standing for those functions. So particle wave duality makes it so that it does give an alternative for a Reichenbach's negative in the mathematical nature of probabilities with regards to quantum mechanics. Well, that's about an hour today. I'll put these books back in the box then. Good day, gentle readers. Reading foundations today. Quantum causality.